Hey everyone, Mr. Montgomery again. Today we are going into lesson number 2 for electromagnetism. So today we're going to be talking about electricity, magnetism, and motion, and what these three things have in common. Alright, so let's review a couple things first from the previous lesson. What is a solenoid? Is it a coil of wire that with an electric current, a surge of power that hits a transformer, or any kind of conductor that is attached to electricity? Okay, a solenoid is the first one. It's a coil of wire. Remember, if it's not a coil, then it's not a solenoid, and it's that coil that makes the electromagnetic field much stronger. Okay, what kind of motion does a magnetic force produce? Is it gravitational motion, circular motion, push and pull motion, or parallel motion? Alright, do you have an answer picked? The correct answer is, well, magnets have a push and pull motion. So they're either going to pull towards each other and attract, or push apart and repel. Okay, last review question. True or false? An electrical current produces a magnetic field. Is it true, false, or just, the anime One Piece is insanely overrated? Okay, do you have an answer picked? Okay, the correct choice is true. Absolutely true. If you have an electrical current, you are producing a magnetic field. So let's jump into today's lesson. After today, you're going to be able to explain how electrical energy can create motion. Not only just that, you're going to be learning that there is a connection between all energy. Okay, so electrical energy and motion. When electricity and magnetism interact, this causes something to move. When an object has the ability to cause movement over distance, we call this force. Okay, I feel like that's already a mouthful in here. I don't want to have to do any extra explaining if it's not necessary. I don't want to overload you guys here. Okay, but if you need another second to read that over, just hit the spacebar, pause the video. Okay, and this next slide, you're probably going to giggle because, I feel this is one of those things or terms where the answer is in the term. So any energy we associate with electricity, we simply call electrical energy. So we might be referring back to electrical energy later on in the lesson. Just know that it's energy associated with electricity. That's it. Okay, so the energy an object has due to its movement or position, we call this mechanical energy. So here's a good example of a hammer and nail. The position of this hammer is changing in order to drive that nail into the wood. And you're probably wondering, why are we going through these random terms? They have nothing to do with each other. Well, it might seem that way, but they're actually going to have some connections very soon. So just know this is a form of mechanical energy right here. Okay, moving on. All right. But think to yourself real quick, what is some work or mechanical energy that you've completed at home? What's something you've done that has changed the movement or position of an object? Any thoughts? Maybe making your bed? Lifting a pillow, maybe? Ooh, here's a good one. Stirring a pot. If you're cooking something, right, you got to make sure you keep stirring it. So those are just some examples. Okay, but energy can be transformed from one form into another. So when it comes to energy, we can always create it. We can transform it from one version to another, but we can never destroy energy. It can just be transferred from one way or one form into another. So in this little YouTube video, you see right here that this guy has a little hand generator, right? And actually has a hand crank down here. As he turns that crank, it will register a voltage on this digital multimeter. And the slower you crank it, the less the voltage that is produced. The faster you crank it, the greater the voltage produced. So, an example of transforming energy from one form into another is mechanical energy being transformed into electric energy, which is what is happening right here. We are using our own mechanical energy, changing the position of this other object in order to create an electrical current. Alright, so you see right here that the person in video is attaching two cables to complete the circuit from the digital multimeter to the little hand crank generator. Because if you don't have the circuit completed, then it's not going to register anything. Remember, if it's not complete, not go from start all the way back around to finish, then you don't have an electrical current. So just showing that the meter is at 0, it's on, it's working, and watch he slowly cranks, you get a small voltage. Crank it very slow, because this actually has a little electrical motor in it using induced current, which we're going to learn about later on. And the faster he cranks it, the greater the voltage. So we're transferring this mechanical energy over into electrical energy, getting about almost 7 volts. And there was another video that kind of shows a really good example of this being vice versa, where we can also take electrical energy and convert it over into mechanical energy. So I'm not going to play this video, but I will explain it a little bit. There is a little electrical motor with a power source connected to it. The power source is just a 9-volt battery. That is then rubber banded to this axle, which then turns the wheels. So by using the energy of electricity, we can then convert it to mechanical energy to make this vehicle move. And you could, of course, make something like this at home as well. You could buy like a little motor like that on Amazon, probably for like $5 or $10 or something. Nothing too crazy. Maybe cheaper, I'm not exactly sure. But when a wire with a current is placed in a magnetic field, the electrical energy is transformed into mechanical energy. And you're probably thinking, where is the magnetic field? It's inside this little motor. This can use an induced current as well in order to get everything done. And also there's always a magnetic field with a battery attached or any kind of electrical current flowing through a conductive wire. So the magnetic field produced by the current causes the wire to move. Well, that can happen. It really depends on what exact device we're talking about. And this is going to be slightly more relevant in the next couple slides when we talk about electric motors. So what do you think a galvanometer is? Oh my gosh, I get tongue-tied with that word. I know some of you guys do too. So a galvanometer, if you haven't seen this lesson before, let's make a prediction. What do you think it's going to be? Is it a machine, a unit of measure, or something that tells temperature? Well, if you don't remember, or if you didn't know this already, a galvanometer it's a machine. And I'm not going to lie, it's not the most exciting machine in the world. But it is absolutely necessary. This device detects little, small electrical currents. And you can even find stuff like this sometimes in, as odd as this is going to sound, there was one of these in a dentist's office. When I got a root canal done, they had to make sure that they got all of the nerve cells out of the tooth, because every nerve cell sends these tiny, tiny little electrical currents. Okay, so inside of a galvanometer, an electromagnet is suspended between two opposite poles, permanent magnets. Okay, so that's the first step of it. We're going to go into this part by part. So first we have this solenoid right in here, right? We have some coiled wire, which is of course going to be copper. We have these two permanent magnets, one on each side, and the power source is going to be out here somewhere. And what happens is when the electrical current starts flowing through here, it disrupts the magnetic field of these two permanent magnets. When that happens, that forces this centerpiece to move, or more specifically, it will wobble. So you'll see that this little needle here will wobble from side to side whenever there is an electrical current sent through here. So, and I'm just kind of, sorry, I might have jumped again a little bit, I might be repeating myself a little bit, but when a current is sent through it, it disrupts the magnetic field and causes the wobble. The greater the current, the more the needle is going to wobble. Okay, so if you had maybe just a little AA battery or something, it might wobble not past these first two lines. But if you were to attach a 9-volt, you're going to, of course, get a greater wobble because it has greater voltage being sent through the device itself. Okay, but what if a galvanometer made full rotations? Well, if that happened, then it actually changes into something else that we use every day too, which is an electric motor. So think about it. If you're able to make full rotations to keep the current consistently flowing, well, then you could have something really cool like a fan or a blender or even an RC toy car, like a little remote control toy car, and even a Tesla. Tesla runs on an electric motor too. So, for electric motor, a device that uses an electric current to turn an axle. So there's an axle in there that is rotating all the time. And let's see exactly what all the little parts are of this one device. Because, you know, it's not going to be as simple as we might think. Well, not at first. But after you kind of just think about it, after you learn all the parts, it does make sense. So we'll break this down part by part. So first we have the brushes, and I have this black arrow pointing to these yellow pieces right here. These are the brushes in the electric motor. So brushes supply current to the armature, but the brushes do not move, and the armature is going to be this wire that's going to be right above here that got cut off. But we will get into that in a quick second. So you have the power source, sends the electrical current through the conductive wire to the brushes, and then sends that current to the communicator, which will transmit it to the armature over here. The armature is between the two permanent magnets. And if you guys remember, when we have this electric current flowing through two permanent magnets, it's going to create a disturbance in the magnetic field and cause these wires to move. That's what's going on. So if there's no magnets here, and you just still send the electrical current through, it's not going to move. It needs the magnetic field to push it away. So next we have the armature, which will rotate by disrupting the magnetic field using the electrical current. So remember, the armature is this wire, this little loop of wire up here that's attached to the communicator. Okay, and last, the communicator reverses the current each half turn so that the armature can spin continuously. And that's it. That's all the little parts of an electric motor, and it's this little simple contraction that gives us a whole bunch of really cool stuff that we like to use, such as toy cars and fans and blenders and all this other kind of stuff that we use in tons of electronic devices. Alright, so I hope that this video was helpful. I helped refresh your memory, maybe even help you study a little bit, refresh on those terms that we were learning about. And as we further go down the line here, guys, with electromagnetism, everything is going to slowly intertwine more and more and more together. So we kind of talked about how electrical currents disrupt magnetism and how that has to do with energy and stuff. And it goes even deeper into the next lesson when we are going to be talking about power plants and inducing currents, which is really, really cool. And that's how we supply all the power to all of our homes and schools and all the buildings in the entire world. Alright, but I don't want to spoil anything. That's what the next video is going to be about. So, again, I hope this is very helpful, guys. I will see you next time, and I hope you have a great day.